Hello everyone, I'm Yang from Tsinghua University. Today I'm going to introduce our work, TeRM, extending RDMA-attached memory with SSD. Let's begin with a brief introduction of RDMA and RDMA-based storage system. RDMA is a widely used network technology. It provides high performance and low latency network connection between the machines. RDMA catalyzes lots of in-memory storage systems, including file systems, key-value stores, and transactional databases. We list some examples here. There are two types of machines in the RDMA-based in-memory storage systems, server and client. A server exposes its virtual memory with RDMA MR. We call the MR RDMA-attached memory in this paper. The server's RNIC pins all virtual pages in the physical memory and builds the RNIC page table. The client accesses the server-side MR by one-sided RDMA read and write. Receiving an RDMA request, the server's RNIC works through its page table to locate the physical addresses of data. Then it transfers data via DMA and bypasses the CPU. RDMA has high performance, but it also requires a large amount of physical memory. As memory is expensive and limited in a computer system, we explore how to extend RDMA-attached memory with SSD. We show an existing hardware solution, ODP-MR, on-demand paging MR. It is proposed by a famous RNIC manufacturer, Mellanox. With an ODP-MR, what you need to do is just mapping an SSD and registering the virtual address area as an ODP-MR. The client submits normal RDMA read or write to access data on an ODP-MR. Let's see what happens on the server side. The slide shows the RNIC page table of ODP-MR and compare it with a CPU page table. The biggest difference between an ODP-MR and a normal MR is that it does not pin all the pages in the physical memory. So in the RNIC page table, not all pages are mapped. The green ones in the page table are mapped to some physical pages. We call them valid virtual pages. The white ones in the page table are not mapped to a physical page. We call them invalid virtual pages. When an RDMA request accesses a valid virtual page, everything goes well. The RNIC follows the virtual to physical mapping and transfers data with DMA. But what if an RDMA request accesses an invalid virtual page? We all know that when the CPU accesses an invalid virtual page, it triggers the CPU page fault. RNIC works similarly. It triggers an RNIC page fault. RNIC solves the RNIC page fault by 4 steps. Step 1A, 1B, 1C, and 1D drawn in the figure. Step 1A, the RNIC suspends the network connection and informs the RNIC driver of the page fault. Step 1B, the RNIC driver interacts with the OS kernel to trigger a CPU page fault. The kernel resolves the CPU page fault. It loads data from the SSD and sets the page table properly. Step 1C. The RNIC driver updates the RNIC page table. The data has been in the physical memory, and so it is ready for the RNIC to access. Step 1D. The RNIC resumes the network connection and the RDMA request. About two other flows, invalidation flow and advising flow. You can find more details in our paper. ODP-MR relies on three flows to keep the RNIC page table synchronized to the CPU page table. ODP-MR is very promising, but our experiments show that it is not the silver bullet to extend the RDMA-attached memory with SSD. Here is an experiment about read performance. We unmap an SSD to get a 64 GB virtual memory area and register it as an ODP-MR. We limit the physical memory to 32 GB, and which is half of the virtual memory. The figure shows the results. The pink bars mean that we do not limit the physical memory, and all pages are mapped in the physical memory. The results show that ODP-MR slows down the performance by over 60 times to about 300 times. We break down the end-to-end access latency. A normal RDMA read consumes only 4 microseconds. Reading an invalid virtual page on an ODP-MR takes about 570 microseconds. We break down the latency into 4 parts. As the RNIC takes 4 steps to resolve an RNIC page fault, we can see that the overhead comes from 2 sources, hardware and software. Hardware steps are 1A, 1C, and 1D. Store and resume the connection, trigger the interrupt, and update the RNIC page table. Software step is 1B, CPU page fault. CPU page fault is very time consuming. We summarize 2 principles to design TeRM. 1. Unload exception handling, i.e., RNIC page fault, from hardware to software. And principle 2. Eliminate CPU page faults from the critical path. Next, we present the design of TeRM. The gray components in the figure already exist in current systems. The red components are added by TeRM. On the CPU, we have CPU VM. We get a virtual memory area by mapping an SSD. The CPU VM serves local accesses, load store from the server-side application. On the RNIC, we have TeRM-MR. It serves remote memory accesses from the client-side application. TLibS and TLibC are server-side and client-side shared library for TeRM. It replaces libIB verbs using LD preload, so that the upper RDMA application does not need any modification and can run transparently. TeRM-MR is at the core of TeRM. We introduce a magic physical page for TeRM-MR. The magic physical page is filled with magic pattern. The picture shows the RNIC page table of a TeRM MR. All the valid virtual pages, the green ones, are mapped to normal physical pages, like in the CPU page table and an ODP-MR. But for all the invalid virtual pages, the white ones, TeRM MR maps them to the magic physical page. Based on this design, an RDMA read on invalid virtual pages can access data without triggering an RNIC page fault. It returns the magic pattern on the magic physical page. In this way, we remove the RNIC page fault from the RNIC hardware. Instead, we let the software to check and handle the page fault. We show how TeRM serves remote memory read based on TeRM MR. Step 1. As a client-side application submits a read request, tlibc submits an RDMA read request to the server-side RNIC. Step 2. tlibc receives the response data. Step 3. tlibc checks whether the data contains magic pattern. If no magic pattern is found, it means all the data are on the valid virtual pages, and the read request completes successfully. Otherwise, if TeRM finds magic pattern in the data, it means some data is on the invalid virtual pages. In this case, TeRM processes the read request by further steps of software RPC read. As the read arrows and components shown in the picture, TeRM uses software RPC read in 3 steps. Step 1. tlibc, the client-side shared library of TeRM, submits an RPC read request. Step 2. tlibs, the server-side shared library of TeRM, processes the RPC read request, reads data, and returns it to the client. Step 3. tlibc receives the data and completes the read request to the application. In this way, TeRM serves a remote memory read request, no matter the virtual page is mapped or not mapped in the RNIC page table. For a write request, TeRM processes it by RPC in 3 steps. Step 1. tlibc submits an RPC write request. Step 2. tlibs writes the data to the virtual memory area. And step 3. tlibc receives the notification and completes the write request to the client-side application. As RPC accesses data on the virtual memory area, how can the access be efficient? An intuitive way is to load and store the virtual memory, but it still triggers CPU page faults. Recall principle 2. Eliminate CPU page faults from the critical path. We propose converting memory load store to file I/O to read or write the SSD. When we unmap an SSD by the LBA range, i.e. logic block address range, for example, from SLBA to SLBA plus length here, we can get a virtual memory range from SADDR to SADDR plus length. For a given memory address ADDR in the RPC request, TeRM can calculate the LBA on the SSD using the equation here. Then, TeRM can read and write the SSD. We propose TeRM I/O to read and write the SSD. It is well known that Linux supports two types of I/O, buffer I/O and direct I/O. Buffer I/O uses page cache, and direct I/O bypasses the page cache. To avoid heavy overhead by the page cache management, TeRM I/O uses two I/O interfaces conditionally. TeRM I/O queries the page cache to learn whether data is cached. If the data is cached, TeRM I/O accesses it by buffer I/O. Otherwise, TeRM I/O accesses the data by direct I/O. So far, TeRM has built an efficient critical path for remote memory read and write. Unfortunately, the design freezes the data layout between the physical memory and the SSD. To tackle the issue, TeRM determines the hotspots with the collaboration between clients and the server. Then, it promotes hotspots on the server side. You can find more details in the paper. We present the evaluation results. We set up an RDMA cluster with one server machine and two client machines. We map 64 GB virtual memory from the SSD and limit the physical memory to 32 GB. We compare four approaches to extending the RDMA-attached memory with SSD. First, pin. We pin all the pages in the physical memory. It is the ideal upper bound of performance because we do not limit the physical memory in this approach. Second, ODP, the hardware solution based on the ODP-MR. We introduced it before. Third, RPC, the software solution. It finishes all remote memory read and write by RPC and access the server-side virtual memory by memcopy. Please note that memcopy may trigger CPU page faults. And the last one, TeRM, is our solution. The first is the read performance. You can see that TeRM surpasses the hardware solution, ODP, by hundreds of times. It outperforms the software solution, RPC, by up to tens of times. TeRM achieves a comparable performance against the pin approach, but uses only half physical memory. Next, the write performance. ODP performance is very unstable and jitters sharply. TeRM outperforms the software RPC approach by about up to 12 times. The performance improvement here mainly comes from TeRM I/O and promoting hotspots. TeRM can also achieve a comparable performance against the pin approach in this experiment. We also test the performance under dynamic workloads. We run the benchmark application by 2 minutes and change hotspots at the 60th second. The blue line is the upper bound, the pin approach. The red line is TeRM. We can see that TeRM outperforms ODP and RPC approaches significantly. Meanwhile, TeRM is very stable. After the hotspot change, it drops by less than 7%, and it returns to the peak in 1 second. Besides micro-benchmark, we also evaluate the performance using existing RDMA-based storage systems. The first one is Octoverse, an RDMA-based file system. It uses RDMA read and RDMA write to access file data. We test the read and write bandwidth of Octoverse. TeRM surpasses ODP by over 600 times and is up to about 7 times faster than RPC. The second storage system is XStore, a key value system. It uses RDMA read to get the data of a key. The results show that TeRM outperforms ODP by up to over 100 times and RPC by more than 2 times. The results demonstrate that existing RDMA-based storage systems can benefit from TeRM. Here is the conclusion. TeRM proposes an efficient approach to extending RDMA-attached memory with SSD. TeRM unloads exception handling from hardware to software and eliminates RNIC and CPU page faults on the critical path. TeRM implements a user space share library to replace libIB verbs and run unmodified RDMA applications transparently. TeRM outperforms the hardware-only ODP MR by up to over 600 times and the software-only RPC approach by up to about 7 times. Thank you.